The purpose of this video is to define the basis of a vector space and to make a distinction between a basis and a spanning set. So the first thing we need to do is recall what a spanning set is. Take S to be a set of vectors in your vector space V. We say that S is a spanning set if every vector in V can be written as a linear combination of vectors in S. So think of the spanning set as being kind of like a set of building blocks, and you need to be able to build everything in V out of those building blocks. There's something important to note though, and that's that your building blocks don't have to be a minimal set of building blocks. There may be building blocks that you don't need. So what I mean is that a spanning set doesn't have to be independent. For example, you can take the four vectors 1, 0, 0, 1, 2, 0, and 0, 2. That's a perfectly fine spanning set for R2 because every vector in R2, which are just vectors, of the form A, B, can be written as some linear combination of these four vectors. But truly, you don't really need 2, 0, and 0, 2. You could get by with just 0, 1, and 1, 0. But that's okay. The four of them are still a spanning set for R2. It meets the definition. Well, what if you want to take a minimal spanning set? Then you want something that spans and is also linearly independent. That is essentially the definition of the basis of the vector space. So we will say that a set in a vector space V is a basis whenever two things are true. First, it needs to span that vector space. And second, that set needs to be linearly independent, so no redundancies, nothing extra. A minimal spanning set is a basis. The canonical example is what we saw above. If you just restricted to 1, 0, and 0, 1, and then excluded 2, 0, and 0, 2, that's your standard basis for R2. We call these the standard unit basis vectors. They're vectors, they form a basis, and the word unit means that they have length 1. The standard basis for R3 is E1, E2, E3, the analogous set of vectors in 3 dimensions. Those examples were fine, but let's look at some non-standard examples. You don't always have to use the standard unit basis vectors to have a basis for R2. So in this example, we're going to look at two vectors, 1, 1 and minus 1, 1. This is also a basis for R2. So let's convince ourselves of this. To see that the set is a basis, we need to know two things. First, that it spans, meaning any vector, x, y, can be written as a linear combination of these two. And we also need to know that they're independent. The good news is we can answer both 1 and 2 with things that we already know how to do. Let's think of item 1 first. We want to see that any vector can be written as a linear combination of 1, 1 and minus 1. And doing that means we're really looking at a system of equations. We want to see that if we wrote this out as a system, we would have C1 minus C2 equal to X, and multiplying through in the second entries, C1 plus C2 equals Y. So, can you solve the system of equations? Great, this is something we can answer with good old Gaussian elimination. The only thing that's slightly different from the types of Gaussian elimination that we've done before is that when we form the augmented matrix, we're going to see some symbols, X and Y in it. So our augmented matrix that describes this system is going to look like 1 minus 1, 1, 1. Those are the coefficients from the C1 and C2. They're also the vectors from up here as well. And then our dotted line will separate us from X and Y. So we do leave the symbols X and Y in there when we perform this Gaussian elimination. So it's going to be a little bit more tedious than normal because we're going to have expressions involving X and Y when we do this. But the sequence of row operations that we perform are going to be familiar, and here they are. So we take our augmented matrix, and as usual, we want to put the thing on the left into reduced row echelon form. So we're going to eliminate this one first, and we're going to take minus row 1 plus row 2 into row 2. When we do that, entries down here are going to be the numbers 0 and 2, and then you just have to take care to keep track of your x's and y's. Minus x plus y goes into row 2, so that's why you see a minus x plus y here. The next step that you would do is determined by the numbers on the left-hand side of what we're looking at. So next what we want to do is turn this 2 into a 1. So we divide row 2 by 2. This affects the numbers as predicted. And then here, you're going to be dividing this expression by 2. Finally, you want to use the one that appears in spot 2, 2 to eliminate this minus 1. And you would do that with row 2 plus row 1 into row 1. And that means in the spot here, we're going to have it be replaced by x plus 1/2 and then minus x plus y. So it's just a little bit more effort to keep track of the Gaussian elimination steps. At the end of this, you get to see exactly what C1 and C2 are, and C1 and C2 are the scalars that solve this vector equation that we started out with. So C1 and C2 are read off of this matrix right here. We see that C2 is 1/2 minus x plus y, and C1 is this expression in x and y. Because remember, x and y are arbitrary. They're placeholders for whatever your vector in R2 is. So if your vector was, say, 7, 11, then you would have 7 and 11 plugged into this equation, giving you your correct C1 and C2 for that particular vector. So anything in R2 can be written because this equation can always be solved no matter what x and y are. So good, we've verified 1. Any vector in R2 can be written as a linear combination of 1, 1 and minus 1, 1. Now we're going to look at 2. Well, we did a lot of Gaussian elimination already, so let's do 2 the fast way. We're just going to calculate the determinant of the matrix and make sure that it's not 0. There are several ways you can check this, but what I'd like to write down is that the vectors 1, 1 and minus 1, 1 are linearly independent because, well, for starters, one is not a multiple of the other, but also because the determinant of the 2 by 2 matrix is equal to 2, and 2 is not equal to 0. So this verifies 1, and this verifies 2 for us in this problem. And so what we've established is that these 2 vectors do indeed form a basis for R2, just not the standard one. So to summarize, in this example, we did a little bit more work than was strictly necessary. We were given 2 vectors in R2. The quickest way to answer the question, like, are they a basis, is just to see whether they're linearly independent or not. If you have 2 independent vectors in R2, they're going to span all of R2. So they're going to be independent. But we did extra work in part 1 because we wanted to see explicitly how to write any vector in terms of this basis. If all you need to know is whether n vectors in an n-dimensional space are linearly independent or not, well, you can just calculate the determinant of the n by n matrix to answer that question. Let's do another example where we do it in a quick check kind of way. So here's a quick example. Here's a non-standard basis for R3. I can take 3 vectors, say 1, 2, 0, 3, 1, 2, and 0, 0, 1, and ask myself, is this a basis for R3? I'm not going to ask, like, how do I write anything arbitrary in terms of this basis, but just, is it a basis at all? And the only thing I have to do to answer this question is calculate the determinant. I should probably jot down the question that I'm answering to make this clear. There we have it. Is this a basis for R3? Okay, so I do my determinant calculation, and I'm going to do cofactor expansion. And I'm going to do cofactor expansion along the last column because it has a 0, and a 1. My entire determinant calculation just comes down to 1 times a 2 by 2, and that gives me 1 minus 6 being equal to minus 5. That is not equal to 0, and so I know that the 3 vectors were independent, and because there are 3 of them in a 3-dimensional space, I must have that they span all of R3, and there's a minimal number of them. I couldn't span all of R3 with just 2. So I have that they form a basis. Let's do one other quickie example too, and let's look at 1x, x squared, x cubed, and x fourth, and see that this is a basis for the vector space of polynomials of degree at most 4. So in a previous lecture, we already saw that these span P4. You can clearly take any polynomial in P4, and this is a polynomial that looks generically like a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th. And this expression right here explains how 1 through x4 span. So what remains to check is that these are actually independent of each other. And this is also really easy to see. So these vectors, and by vectors I mean these monomials, they're independent in this vector space because The only way you can add them all up together in a linear combination and produce the zero vector is if all of the coefficients are equal to 0. And that is what it means for them to be independent. So let's now look at a theorem. If you take a set of vectors, this set is a basis, then every vector can be written uniquely in terms of that basis. So bases are not unique, but once you've fixed a basis, the expression of a vector in terms of that basis is unique. It's not hard to prove this statement. Let's go over a sketch of the proof. So let's assume for a contradiction that the expression in terms of some basis is not unique. That would mean if you got some sort of vector v, you can write it as one linear combination in terms of v1 through vk, and then a different linear combination. The v1 through vk's are the same, but it's the coefficients that you would arrange to be differently. If you had these two different expressions for v in terms of v1 through vk, then you could subtract the second equation from the first equation, and that would give you the coefficients being subtracted because you're subtracting these component-wise. So c1 minus b1 would be the new coefficient of v1. But because this is v minus v, this would all work out to be the zero vector. But this is no good. S was supposed to be linearly independent. There's not supposed to be a non-trivial solution to the homogeneous equation. But what we're staring at right here is a way to add up v1 through vk with these special coefficients given by c1 minus b1, which is just a number, and c2 minus b2, and so on and so forth, some combination that gives us the zero vector. Either you have contradicted that S is linearly independent, or you have that all of the ci minus bi's have to be equal to 0. But what does that mean? That means all of the ci's equal all of the bi's, which meant that actually these were the same expression to start with. Either way, you've shown that your basis expression in terms of this basis is unique. So that's the important remark to jot down. Bases themselves are not unique. In the previous examples that we did, we looked at non-standard bases for R2. But once you fixed a basis, the representation of your vector is unique. There's a useful couple of facts that go along with this discussion of bases. And the first is if you have a basis, and the basis involves n vectors. If you take any other set that has more than n vectors, it's got to be linearly dependent. This set will have some baked-in redundancies. And then the second useful fact is that all bases have the same number of vectors in them. So if V has a basis with n vectors, and any other basis will also have n vectors in it. Because the number of vectors in any basis for a vector space is always the same, we're now prepared to define dimension. Dimension is another one of these concepts that we have an awareness of and we use and talk about. For example, R3 being 3-dimensional or a plane being 2-dimensional. But now we can really define what it means for a vector space to have dimension. So we will define the dimension as follows. Suppose a vector space, V, has a basis with n vectors. Then n is the dimension of V. Our standard examples, R2 is 2-dimensional, R3 is 3-dimensional. The vector space of polynomials of degree at most n is n plus 1-dimensional. If the n plus 1 is tripping you up, just remember how we index polynomials. A naught x to the 0 plus a1 x to the 1. Our constant term is really x to the 0, so we're counting starting at 1, going out to an x to the n, and so that's where that extra 1 comes from. And the dimension of the vector space of matrices that are m by n is dimension m times n. Dimension is already something that we have intuition and understanding of, but now we have something formal that we can write down and check in an algorithmic way. So this next example that we're going to do is pretty algorithmic. For this example, let's take something that at first glance might look a little bit different. We're going to find the dimension of the span of a set of vectors. The set of vectors that we're going to describe is going to look like this. We're going to take tuples that have as entries d, c minus d, and c. where C and D are real numbers. So what kind of vectors are we looking at here? It might be helpful to use some actual numbers to get a feel for it. C and D are supposed to be real numbers. So for example, we might take C equal to 1 and D equal to 5. That would mean I would be looking at something like 5 minus 4, 1. And that would be a tuple where I have 3 numbers, so we're talking about something that's in R3. So the first thing for me to notice is that I'm talking about a subspace of R3. And remember, the span of a set of vectors is always a vector subspace. So this is a vector subspace of R3, and because of that, it could be 1, 2, or 3-dimensional. Something that I visualize as a line through the origin, a plane through the origin, or all of R3. And it won't just be the 0 vector, because I could obviously take numbers like the ones I took over here that are not equal to 0. So what I need to determine is which type of subspace of R3 this actually is. So let's notice something else. So if I'm looking at my vectors in column form, then that's a little bit easier to see that the vector D, C minus DC, could be written as 2 things added together. It's the D part added to the C part. So in other words, D minus D0 added to 0, C, C. And D and C are numbers, so let me write them outside as scalars. So this is a linear combination of the vectors 1, minus 1, 0, and 0, 1, 1, after they've been multiplied times these arbitrary scalars C and D. Any vector of the form of something in S can be written as a linear combination of minus 1, 1, 0, and 0, 1, 1. It's a little easier to understand what's going on now. These 2 vectors are linearly independent. One is not a multiple of the other, and that's all I have to see since there's just 2 of them. So my span is 2-dimensional. These are a spanning set, and they're a basis of a 2-dimensional space. I'll write that because they're linearly independent. So the dimension of the span of S is 2. It's some 2-dimensional subspace of R3. Let's now do a second example. So here we're going to try and figure out what the dimension of a set of vectors is, the dimension of span S, when S is explicitly these 3 vectors. So nothing fishy here. We've just got 3 vectors, and we notice that these vectors are in R5. These vectors live in R5 because each one of them has 5 entries, but we're dealing with a set of 3 vectors. Now, these 3 vectors couldn't possibly span all of R5. They're either going to span a line, a plane, or a 3-dimensional subspace of R5, depending on whether they are independent of each other or not. So this is not something we can check by calculating a determinant. We're going to need to use Gaussian elimination in order to see the relationship between these vectors. All right, there's a couple of Gaussian elimination steps to do. I would be using my 1 in the first entry as a pivot to eliminate the 2 and the 5 in the first 2 steps, which are consolidated into 1 here. And then from there, I would be adding rows together and doing linear combinations in order to clear out the last 3 rows. So I'm not actually writing out all the explicit steps here because I want to point out that the highlighted rows, 0, 6, minus 6, and then 0, 16, minus 16, and then 0, minus 2, 2. These are all multiples of each other. I could carefully write out the exact linear combination that would be used to clear them out, but because they're clearly multiples of each other, even if it's a fractional multiple, I know that it's going to turn these last 2 rows into all zeros. And that gives me the matrix that I see here. Then the last row operation is going to be to take minus 3 row 2 plus row 1 in order to get rid of this 3 that shows up here. And after that, I'm left with a matrix that looks like a standard unit basis vector from R5, another standard unit basis vector from R5, and then something else. So I have here an independent vector, and then a dependent vector. And it's easy to read off from this form what the relationship between these 3 column vectors is. In particular, what I see is that column number 3 is minus 2 times column 1, minus 1 times column 2, added together. And columns 1 and 2 are linearly independent. So 3 depends on 1 and 2. 1 and 2 are independent. So overall, even though I had 3 vectors in R5, they only spanned a 2-dimensional subspace. In other words, a plane that lives in R5. The dimension of the vector space, which is span S, is 2-dimensional, even though it lives in R5. It's helpful to think of just another 2x2 example. So I'm going to ask, just with pictures, which set of vectors spans R2? And in my pictures, I have pairs of vectors that are either different or the same, and by the same I actually mean are scalar multiples of each other. So this pair of vectors do span R2. These vectors are linearly independent. One is not a multiple of the other. These pair of vectors do not span all of R2, and they are scalar multiples of each other. So visually what I see is that these span a line. The only thing I can get by adding combinations of them together is other things that live on this exact line. So they span a line that goes through the origin. But to truly describe this line that goes through the origin, I still need 2 coordinates. I still need an x and y value. So even though this line lives in R2, it's just a 1-dimensional object. But the pair of these vectors can be used to produce any other vector in R2. So if I think about some favorite or arbitrary point that lives in R2, maybe the point that I want to pick is going to be this point in red. How do I produce that point, which is itself a vector in R2? How do I produce this vector out of the 2 blue vectors? Well, I imagine that I'm scaling the blue vectors out in order to see the red vector as the diagonal of the parallelogram that's formed by the 2 blue vectors. So if I scaled the first blue vector out a little bit further, let's use blue, and if I scaled the second vector out a little bit further, then these 2 vectors would form a parallelogram, and the diagonal of that parallelogram would be the red vector. This is a kind of geometric picture of how these 2 vectors, which are independent of each other, actually span R2 and how you can produce something in R2. If you wanted something to go along with this picture that looks more like an equation, well, we could give some names to these vectors, say v1 and v2, and we're scaling them some amount. It looks like we're taking about 1.5 times v1 and adding it to maybe twice v2. And that seemed to be the combination that produced for us w. And the point is that these 2 vectors are independent of each other, and there's 2 of them living in a parent space, R2, which is of dimension 2. And so we see that any other vector in R2 can be written as a linear combination of these 2. And that is what it means for them to really span this space.